Hi class and welcome back. We're getting towards the end of the course here. Chapter 8, the lithosphere, and then chapter 9 where we look at plate tectonic theory. So chapter 8, we're going to discuss the lithosphere. What is a lithosphere? What are the different layers of the earth, etc. And we're going to finally update our definition of lithosphere. In the past, we just said the lithosphere is rocks and soil and sediment. That's what the lithosphere is composed of, but there's a more technical definition, which you see on this slide here, crust and uppermost mantle. That doesn't mean too much to you right now, but it will do in a few minutes. So this is part 1. We're going to divide this chapter up into 2 narrated versions, part 1, part 2. So here we go, part 1. So we're going to look inside the earth finally, from the surface all the way down to the center of the earth. And if you recall from the first lecture, the size of the earth, well, if we measure the radius, so the distance from the outside edge of the earth to the center of the earth, that's about 4,000 miles. Now we know a lot about what's going on inside the earth. However, if we look at the deepest we've ever sent anybody into the earth, that would be about 2.5 miles or so, about 3.9 kilometers, the world's deepest active mine in South Africa. And the deepest we've ever drilled is about 12.3 kilometers, let's say 7.5, a little bit more than that, miles deep into the crust of the earth in Russia. That's the deepest we've ever gone. So let's say 12.3 kilometers, about 7.5 to 8 miles. How much further to go? Well, if it's 4,000 to the center of the earth, we've barely scratched the surface. So how on earth do we know what's going on inside the earth? And we seem to have a pretty good idea about what is inside the earth. Well, there are several modes of evidence or lines of evidence for this. First of all, what comes out of the earth tells us a little bit about what's inside the earth. So when we have volcanic eruptions or maybe even the gases emitted in volcanically active areas, we can sample those gases. We can sample magma coming up from below. That will tell us a bit about what's going on. Also from physics, we know that when the earth first formed, the heavier elements settled towards the center of the earth. We have more gravitational pull towards the center of the earth than we do on the outside, because the center of the mass is where the center of the gravity will be focused. So we have those ideas, but also the majority of our intricate knowledge is coming from the analysis of seismic waves. So whenever there's an eruption, an earthquake, a large explosion, anywhere on the surface of the earth, waves are going to travel through the earth, sometimes reaching the other side and sometimes not, based on the nature of the wave. Well, the fastest moving waves that would arrive at a receiving station with a seismograph on the other side of the planet, the first waves to arrive would be primary waves. And those are waves that travel like a pulse of energy. So if you look at this way, poof, 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 a pulse of energy going through the earth. On the other hand, we have secondary waves called S waves, like these waves here, that travel in a pattern like this. So the energy is moving in this direction, but there's a up and down component to that wave. Those travel a little bit slower. We call those secondary waves. The first ones I described, the fastest ones, are called the primary waves or P waves. Now, we could also see that S waves do not travel through liquid layers. So S waves, if there was an earthquake here, S waves could get received at receiving stations all the way across the surface of the earth until about here. And from this point all the way over to this point, there would be a shadow zone for S waves. So they just don't get received. In that case, we know that this absence zone that we see right here, this shadow zone, would map out a liquid zone within the earth. So we know then that we have a liquid zone inside the earth. We also know that that's probably made of very heavy elements from the initial formation of the planet. So we can start to map out liquid zones, solid zones, and also the nature of the waves. The denser the material, the wave will travel a little bit faster. The less dense, the waves will travel slower. So we can analyze through computers what the density of that material probably is, and we can also analyze from S waves and P waves where the liquid zones exist. That allows us to map out, again, every time we have a different event, it'll map out the edge of this liquid zone here. So again, primary waves are traveling sort of in a straight line here. If you had a slinky and you push that slinky, the wave would travel through it like a P wave. However, if you got the slinky and you move it up and down and up and down and up and down, it will create things like secondary waves here. So a very different type of wave, moving a little bit slower. So those two waves, by analyzing them, which are created when we have an earthquake, we can kind of map out what's going on inside the Earth. What does it tell us? Well, basically, we do have different layers. We have this outer solid shell layer that we call the crust. We also have a zone which occupies a great majority of the planet called the mantle, mostly solid, but it has flexible qualities to it, little plastic qualities in some areas and semi-brittle in other areas. Then we have a liquid zone. This is referred to as the outer core. That's our only liquid layer. And inside that, the pressure is so great that we have an inner core which is solid in composition. So we've got solid, liquid, mostly solid, solid. Crust, this is referred to as a mantle, outer core, inner core. So we analyze all the details we can from these seismic waves and any kind of gases or liquids emanating from below coming up towards the surface, and we can map out and make a very nice diagram of what we have for the different layers of a planet. So our outer layer is referred to as crust. So we have this outer layer which is solidified, so it is solid, but the crust comes in two varieties. It comes in thin crust and it comes in thick crust. Well, the thin crust is probably 5 or 6 miles thick on average, and that is called oceanic crust. It's usually dense, made up of darker minerals, or the rocks are made out of darker minerals. We refer to these minerals as mafic minerals. That means they're rich in magnesium and iron. And a very typical mafic rock would be basalt. We're going to learn more about basalt later in the chapter. Our second type of crust is referred to as continental crust, and that can average about 20 to 25 miles thick, thinner in some places, much thicker in other areas like above and below mountain chains. So as mountains rise, their roots also get deeper, so it can be very thick under mountain chains. And this continental type of crust is referred to as felsic. So it has iron, silica, and oxygen, and also aluminum. So we have very lighter elements making up, lighter minerals making up these continental rocks. A very typical rock of continental crust is granite. And again, we'll learn more about these rocks later in this chapter. Now, at the base of the crust, be it oceanic crust or continental crust, analysis shows that seismic waves passing through all of a sudden speed up. And that tells us that we have left the crust and entered the next zone, referred to as the mantle. So the zone where we leave the crust and enter the mantle is referred to as a discontinuity. And this one's referred to as the Mohorovičić discontinuity, otherwise known as the MOHO. So that just represents a line separating the crust from the mantle, where the materials of the mantle are a lot more dense and those seismic waves sped up. So from the base of the crust, be it oceanic or continental crust, we go deeper than that, we're now into the mantle. But the mantle has this more iron rich and magnesium rich chemistry to it. The typical minerals, if we took the average chemistry of the mantle, it would make the mineral olivine and the mineral pyroxene. So olivine and pyroxene are They tend to be darker in color. In fact, olivine tends to be like those darker greens, grays, and blacks in color of certain olives. Pyroxene, the first four letters there, pyro, this comes from fire. So basically these are associated with eruptions of mantle-rich material coming up towards the surface of the Earth. So the entire mantle has what we refer to as an olivine pyroxene chemistry. The mantle is divided up into three distinct zones. And the top zone we call the uppermost mantle. So the uppermost mantle goes from the bottom of the crust to a depth of about 40 miles. These are very average numbers I'm giving you here. It's not the same everywhere on the planet, but these would be pretty typical numbers. So let's say from the base of the oceanic crust down to about 40 miles. Base of the continental crust down to about 40 miles below the surface. And this uppermost mantle, again with olivine pyroxene chemistry, is solid and it is glued to the crust. So the crust, whichever type of crust, and the uppermost mantle act as a solid unit of rocky material down to about 40 miles on average below the surface of the Earth. So again, we've got solid crust, solid uppermost mantle. The next zone is critically important. That is referred to as the asthenosphere. The asthenosphere is found from about 40 to 200 or more miles below the surface of the Earth. And this is referred to as a plastic zone. Now, plastic is kind of like taffy. You can pull it. It can be bent. It can be pulled. It can bend. Maybe like if you put honey in the fridge and then try to pour out the honey. It would come out, but it would move very, very slowly. And if you made it very cold, it's sort of solid, it's sort of liquid, it's sort of in between. We refer to that as a plastic consistency. This is not where your recycled materials go to. This is just a word that tells you that this stuff can be bent, it can be deformed. Now that's going to be important a little later on. So imagine what we have now is solid crust, below that solid uppermost mantle, and below that this gooey layer. So everything is sitting on top of this gooey layer. And if that gooey layer moves, which we'll explore later on, the stuff above it, of course, can also move. Okay, our last layer within the mantle is referred to as the deep mantle. So the deep mantle goes from about 200 miles below the surface to 1,800 miles below the surface. And since this is on the outside of the Earth, it occupies an enormous volume. Over 80% of the volume of the planet is occupied by the mantle, and the greatest majority of that is found in the deep mantle. So again, 200 miles to about 1,800 miles below the surface of the Earth. Now, when we get to 1,800 miles below the surface of the Earth to 3,100 miles below the surface of the Earth, we are in the area of the outer core. Now the core is made up of the heaviest elements that were around at the time of the formation of the Earth, so basically iron and nickel. We know that those gravitationally were pulled towards the center of the Earth. We know that we have a liquid layer here because those S waves disappear at 1,800 miles. We also know that based on the pressure we find about 3,100 miles below the surface, that the iron and nickel cannot exist as a liquid. There's too much pressure. It makes it squished into a solid. So we have the outer liquid iron and nickel core, the outer core, 1,800 to 3,100 miles below the surface, followed by the inner core, about 3,100 miles to the center of the Earth, some 4,000 miles below the surface. Of note here, the outer core, that liquid layer with the iron and nickel, has convection cells of iron and molten nickel rubbing past each other very ferociously. And whenever you get iron rubbing past iron, it's going to generate a magnetic field. So this is where the Earth's magnetic field is generated, and that's what sort of protects us from the damaging elements of the solar wind. So those gamma rays and beta rays, cosmic rays coming down, raining down every now and then from the sun towards the Earth, get basically directed away from or around the planet by our magnetic field. So what we just discussed, now we see here in a graphic form, we have this crust on the upper level here. And remember, we have oceanic crust and continental crust. Very difficult to see at the scale, so I'll have to blow this up in just a second. Below the crust, we have the mantle. Remember, we've got the uppermost mantle, then we got the middle mantle, and the great majority of it is the deep mantle. Then we have the outer core, iron and nickel, liquid, from about 1,800 miles below the surface to 3,100 miles below the surface. And then we finally have the solid inner core from the center of the Earth, 4,000 miles below the surface, to that 3,100 mile boundary. So those are the layers inside the Earth. You see various images of that. Now remember, at the very surface, again, we had the crust, continental crust. Those are those felsic rocks like granite, averaging around 25 miles thick. We had the oceanic crust, 5 or 6 miles thick, those mafic rocks like basalt. And because this was more dense, sits lower, when the oceans precipitated out, basically they went to the low spot. So the oceanic crust underlies the world's oceans. Then we have that line that we can tell the crust has ended, seismic waves speed up. That's the MOHO, or Mohorovičić discontinuity. Below that, we have the uppermost mantle with olivine and pyroxene chemistry making up the minerals in the rocks. Interesting to note, uppermost mantle, solid. The crust, solid. They are glued together, and they will move, whenever they do move, as a unit, broken up into small blocks. And by the way, crust plus uppermost mantle is referred to as the lithosphere. So the true definition of the lithosphere is the Earth's crust and uppermost mantle. Below that, we have that gooey layer of the asthenosphere, the plastic sphere. That can be deformed. It can bend. And within the asthenosphere, we've got convection cells. So these rocks move. They move up, down, sideways. And imagine if these rocks can move very slowly on the order of centimeters to a few meters per year. If they do so and they convect, they get sticky towards the top, they're going to drag this uppermost mantle off to the side, allowing mantle and crust to move. So this zone here will become very important when we talk about plate tectonic theory. Below that, we have the deep mantle. The deep mantle goes from about 200 miles below the surface to 1,800 miles below the surface. But again, this was too small to see on the earlier diagram, so I had to blow that up to see it up close. Use those minerals of the mantle, olivine and pyroxene. You can kind of see why olivine gets its name, and pyroxene, those darker colors here, representing high concentrations of iron, magnesium, etc. So again, Earth's interior, we've got the core. Remember, two types. We've got the solid inner core, the liquid outer core, and then the mantle, which has these convection cells in it, and some localized ones within the asthenosphere. And the asthenosphere is going to drive the plate tectonic motions we will talk about in our next chapter. Again, other looks at this. We've got crust on the outside here. This is our crust. We've got our mantle, and we've got our outer core, which is liquid, and the inner core, which is solid. I think you have the point now. All different views. And as I mentioned before, that outer core, that molten layer within the Earth, is what's going to protect us from those solar winds. So very hazardous elements heading towards the Earth, and the Earth right here with this magnetic field shielding the Earth from those solar winds. And if those interact with the particles in the upper atmosphere, we get a beautiful aurora, like the aurora borealis, caused by that. Now I'm going to focus on the crust for just a moment. So the Earth's crust, there are about 90 to 100 common elements, atoms, if you will, within the Earth's crust. And a few of them, probably 8 of them, represent 98.5% of all of the elements within the crust. So those elements, or atoms, they will combine. Let's say if they're molten, they'll combine and slowly solidify to make up minerals. So 90 or so somewhat common elements will combine to make 4,000 or more minerals. So minerals are the solid result of the solidification of elements that have been in a liquid state and finally they have solidified into these minerals. Examples would be things like feldspar, quartz, olivine, pyroxene, etc. Now, once you have minerals, those will bunch together to create different types of rocks. So the order is elements make up minerals, minerals make up rocks. So if we have 90 or so common elements making up about 4,000 different types of minerals, minerals of all kinds will combine to make a certain type of rock. Well, there's going to be countless numbers of rocks. It would be mind-boggling to know every single type of rock that there is because of so many different varieties. So we have to make sense of that. What we're going to do a little later on is say, well, how do those rocks form? What mechanism is there to form those rocks? And that's how we will base our rocks into 3 main categories. Again, that's coming in a few minutes. So the most common elements in our crust. A lot of people are not aware that the most common element or atom that makes up the minerals and for the rocks of our crust, oxygen. Almost half of the typical rock or mineral is made up of oxygen. Look at that, 46.6%, followed by silicon and then aluminum. So oxygen, silicon, aluminum, the 3 most common elements in our crust, followed by things like iron and calcium, sodium, potassium, magnesium, etc. And again, just those 8 make up 98.5% of the elements in the crust. Now, no one ever remembers who came 4th or 5th or 6th or 7th or 8th in the last Olympics, in the 100-yard dash, let's say, the 100-meter dash. You might remember the gold medal winner, the silver medal winner, and the bronze medal winner. So in red here, the top 3 probably worth remembering. The minerals that we just talked about will create certain types of minerals. So elements make up minerals. And these minerals, again, quartz, feldspar, olivine, typical minerals. Each of those have a different chemistry, and we'll see a little bit later on a different way of forming. And these minerals, these 4,000 or so named minerals, will make up countless numbers of rocks. And again, there's so many, we just have to say, let's base the rock classification on how the rocks form. And we're going to address that a little later on. So before we do that, some key rock terms. I do need you to know these 4 terms. They're pretty straightforward. Bedrock means rock units found near the surface of the earth. So you dig down, you get to rock, that's bedrock. You go to the mountains, you see rock, that's bedrock. An outcrop is bedrock exposed at the Earth's surface. You don't have to dig down to see it. So if you ever see a steep mountain cliff, and that's exposing bedrock to the air, that bedrock exposed to the air will be called a bedrock outcrop. Magma is liquid rock found below the surface of the earth. So again, liquid rock below the surface of the earth is referred to as magma. But if that magma bubbles up to the surface of the earth and then flows out along the surface of the earth, we would then refer to that as lava. So the difference between lava and magma, magma is below the surface of the earth and lava is on the surface of the earth. So all lava used to be magma, but not all magma will become lava because much magma just stays below the surface. Okay, bedrock, rock near the surface of the earth. A lot of times bedrock is covered over by pieces of rock that got weathered and eroded away, maybe from up here, and then rolled downhill and started to cover over some of this lower bedrock. So these are sediments right here. This pieces of rock, again, sediments over here. So if you were located right here in the middle of this valley, you'd have to dig down to get to the bedrock. Or walk along the valley, up the slope of the mountain a little bit, and then you might get some bedrock exposed up here, in which case that would be called an outcrop. So an outcrop is bedrock exposed to the air. Okay, bedrock and outcrop. So an outcrop is indeed made out of bedrock. It's just that you can see it without having to dig down. Magma found below the surface of the earth, if it finds its way up to the surface and starts to flow on the surface of the earth, is now referred to as lava. Big difference. Magma, if it stays down here and starts to cool, it's going to take a long time to cool because that energy, that heat has to make its way out through all those rocks here. But lava is going to cool a lot more quickly. Major earth materials. Sediments. Sediments are pieces of rock. They were weathered or broken up and then removed and deposited away from bedrock downhill. Tephra, fragments of rock blasted out by volcanic eruption, blasted into the air where what goes up must come down, so they fall down to the surface of the earth. Soil is a mix of rock fragments and air and water and organic materials. Basically rotten rock. It takes a long time for that rock to rot away to form that soil. And finally, we've got rocks. Those are solid mineral matter that we find within the Earth's crust. And we're going to discuss these in order. First of all, sediments. So again, sediments are pieces of rock. They were broken from larger pieces of rock, which then get removed by wind or water or ice, always moving downhill. Gravity will pull them downhill. So it's removing, let's say, pieces of rock from the mountains and moving them down into the valleys as sediment. So they have to be removed or eroded, transported downhill, and finally deposited into low spots. So here we see sediment being deposited on a beach, as in here. Sometimes sediment in a riverbed, so always a low spot. Now these can pile up over time. These sediments can pile up and pile up and pile up. And so the ones towards the bottom can get really crushed by the ones on top of them, and they can get crushed back into rocks. So sediments have names based on how big the pieces are. A tiny piece of rock is just called clay. Now, if it's clay with some silt and it's in a wet environment, we call that mud. But the size of the grain is referred to as clay, the finest of the grains. A little bit bigger piece of rock we call silt. A little bit bigger we call sand. So sand is just basically a piece of rock between 1/16 and 2 millimeters in size. That's all sand is. Sand is a tiny piece of rock within this size range here. Bigger than sand, we have gravel. And bigger than gravel, we could break that down, the gravel, into pebbles, cobbles, and the biggest, boulders. Or you can just refer to all of that as little gravel and big gravel, or fine gravel and coarse gravel. So basically, clay, silt, sand, gravel, and let's add boulders. That's going from finer pieces of rock fragment all the way through to larger pieces of rock fragment. Later on, we're going to talk about some of the, remember if those same grains or fragments are allowed to be compacted together back into rock, these are the types of rocks that they will create, but we're getting ahead of ourselves here a little bit. Tephra or pyroclasts, these are the rock fragments blasted into the air during a volcanic eruption. Okay, technically, while it's up in the air, we could actually say that lava bombs and lava blocks and ash, these would be considered to be tephra also. Now what goes up must come down, so you can get thick accumulations of ash deposits and lava bombs deposited in the splatter zone around a volcanic eruption. Hard to see in this diagram here, but basically ash and larger ash, which we call lapilli, and lava bombs are the majority of the tephra coming out of a volcano. So a lava bomb, that probably came out as a liquid, went up into the atmosphere, comes down and splats. If you got hit by one of those, there's no coming back from that. Lapilli means little stones, so that's like little cinder-sized pieces of rock that go up, come back down. And then ash is the finest of the material. Blown up or blown out. That's pulverized rock, basically, blown out by the volcano. And that might take a long time. It might take weeks, might take years for that to come back down, circulate around the globe. There were eruptions of Krakatoa in the 1880s, and it took 2 years for that ash to work its way out of the atmosphere. So we have brilliant sunsets in various places around the Earth for those 2 years. Soil, that rotten rock, the decomposed rock, always has four major components. It's gotten the parent material, the base material, the pieces of rock themselves. The spaces between those rock fragments cannot be occupied by water or air, and there's always some organic material that is a component of a soil. We can see here that soil develops distinct layers, which we call horizons, with a very, very thin layer of organic material, then an organic rich layer, and then layers where we've seen the organics be washed out or leached out, send down deeper towards that parent material. Now, we're not going to talk about, you don't have to know the specific horizons for your upcoming test. Just be aware that we have these. I've included a video for you to learn a little bit more about them, just so you're aware that soil has these very specific layers or horizons, each one with its own characteristics. So again, the main component of a soil, a typical soil, would be the mineral matter. This is why we talk about it in terms of being part of the lithosphere. But there's a little bit of atmosphere in a typical soil, a little bit of hydrosphere in a typical soil, and a little bit of biosphere in a typical soil. Just the majority of it is rock particles, so we usually assign this to the lithosphere. The fragments, individual fragments that we talked about, their textures before. Remember, clay is the smallest grain size. Then we have sand, and over here we have silt. And the clay, silt, sand components would, based on what percentage you have of each of those, would tell you what specific type of soil you would have. So if it's largely almost all clay, we call it clay. Almost all sand, we call it sand. Almost all silt, we call it a silt. But if it's a mix, it could be a sandy loam. Loam meaning mix. It could be a sandy clay, half clay, half sand, thereabouts. It could be a silty clay. And that's important for agriculture because soils need a couple of things. They need the clays because a lot of nutrients are attached to the clays. But if it's all clay, we're going to have a problem because the soils don't drain very well. So if you have a good mix of some clay, some sand, some silt, you've got good drainage, good access to nutrients, and every plant has different nutrient requirements. So certain plants are going to grow well on certain types of soils and not on others. So in soil science, there's a lot to it. You could also look at this from a construction point of view, that if you have a clay soil and you want to build a house on it, you've got to check because sometimes clays will absorb water and expand. So if you build part of your house on a clay soil that's an expansive soil and part of your house on a sandy soil that doesn't expand, if you do any kind of irrigation or if it gets wet around there, part of the foundation could be lifted up and the other part not, and your house will crack up in half. So whenever you build houses, especially in Southern California, you have to check the soil to make sure you don't have any expansive clays there. There's a lot more to that also, but you can see that soils and knowing more about soils can have some far-reaching implications. So that's the end of part one. We still have to talk about the earth materials of rocks. There's a lot to that, so that's going to be coming up in part two. So in part two, we're going to discuss the three major types of rocks and how one type of rock can become another type of rock, given enough time. So that was enough of an intro for you for now. More to come. We'll see you soon enough. Take care. Bye-bye.